哎，这个好了，这个好了。这里。改过了，把那个，对，把那个。
Yep. So this is something I've been looking for someone to do. Can I talk to you more about that?
Just in that.
你们那个可以微信，对。
Hello. Okay, so we'll start our panel discussion. So we have heard the very informative talk by Dr. Wang. It was really eye-opening. We can see HKO really kind of at the front of our exploration of using AI for nowcasting of severe weather. So this session will talk about more in-depth of this topic. So first, I'd like to introduce our panelists. So besides Dr. Wang, we have Mr. Professor Qingming Shang. He was the director of Hong Kong Observatory and also expert on aeronautic meteorology. And also we have Professor Shuaiqi Tang from Nanking University, Department of Atmospheric Sciences. Professor Tang actually specializes in using observation to improve a climate model. He has a very extensive experience using DOE's ARM data. Actually, he came from Pacific Northwest National Laboratory from US, and now associate professor in Nanking University. So for this panel discussion, I will first ask a few burning questions, then we'll open the floor for all the audience to ask questions. So, so we heard this very enlightening lecture by Dr. Wang. So I feel actually there are really explosive adoption of AI in nowcasting, in weather forecasting. So, but we've seen a lot of impressive models developed by major tech companies like NVIDIA, Google, and Huawei in China. So I feel like for professionals in government and also in academia, so we actually also study weather and want to do better weather forecast. But now the tech companies, they are very wealthy, have a lot of resources. Now also enter this field and have delivered very good results. So I want to ask our panelists, do you feel like there's a threat from the tech companies and also doing weather forecasting? So how do you feel this is an opportunity or a threat to us, like in academia or government specializing in weather forecasting? Or what a recommendation you would have for government and academia, like scientists in this field, to actually embrace this technology of AI and to advance our field? So maybe we'll start with Dr. Wang.
Okay. I think it should be my director should be much more better position than me. Well, I think I will talk from forecaster perspective first. Because actually we see a really quick rising of the AI meta model, the big model, like Fuxi, Pangu, AIFS or some others. And they really do very powerful simulations. And from forecaster perspective, the result is everything. We do verification. And I think we have a couple of published papers recently by our director now that we verify the performance of AI weather model for tropical cyclone threat forecast. It's quite good, competitive with the traditional or the physical full physics model. And so they have a very strong point on improving our weather forecast. But of course, it's a challenge now because they can do everything. That no need weather service. But the point is, they still suffer quite some important issue. For example, when we talk about tropical cyclone, threat looks quite good because they manage to do the simulations by representing the general steering flow, the big pattern of atmosphere. And because they have a very good reanalysis data. I always say because they have very good reanalysis data, so observation data is the 0.0 important thing for doing AI. So they have a good data, so they learn the model very well, but the formalism itself, I think there's still a lot of room ahead in terms of, for example, the intensity, the wind structures, which is very crucial for us to consider hoisting or issuing what kind of typhoon signal. Rainfall is still a big challenge, and I think nowcasting AI still has a really big room for us to beat against them if we can extend the skill even for 12 hours, or with some physics-informed approach can extend to 24 hours. And I think we could have still a lot of way to have advantage for that. But as a forecaster, I would see there's a lot of opportunity because it really gives us a lot of really useful data for us to understand the changes and the reason behind why they can forecast certain kind of thing. Because just like one of the questions they during my talk at the end, that it's not very easily explainable why one will work not for the other. But when you do the verification and when you do day-by-day inspection, you will know, okay, this kind of model based on that kind of approach, that kind of formulation, they have the strength and certain kind of weaknesses. So we understand better why different AI weather model formalism will do. The other advantage is because they have a lot of resources. So somehow, maybe if we can find a way to partner with them, to harness their resources, then we can improve ourselves. And that's why, as introduced by Professor Su at the beginning about myself, I'm also one of the chair of the expert team on the, you can now call the WMO Integrated Processing and Prediction System. In old days, it's GDPFS. So this is a way that we have tried some other way to formulate some pilot project. And there's now a pilot project including a lot of weather agency. And we also try to explore the PPP approach, the private partnership, public sector private partnership. So in that way, we involve Google, we involve Microsoft, we involve some other big giant. Hopefully, they will provide us at least resources for training our AI model. And that will be useful because we can maybe deploy our model on their cloud system and then make real-time prediction, or at least some test bed of prediction for supporting those countries may have difficulty in catching up in using AI. Yeah, so I think Mr. Xiong may have even some more big idea.
Thank you for inviting me here. Apart from being the former director a few years ago, I'm also at the UST working on climate modeling and resilience studies. So, but I think I could speak from the perspective of user rather than practitioner in AI, is that I think every opportunity comes with a threat. I think they come hand in hand. So it depends on how we are going to capitalize on this. And I definitely agree with Wai Kin that we need to seek a close collaboration with the commercial players, as they have already made a headway to show us that AI weather models is having superior performance than our conventional physical models. So even though it looks very well, too good to be true, from my perspective, being a forecaster for 30, 40 years, but still we can't deny the fact that they have better performance metrics. But the question, I think, for example, as a director who has to determine on the spot whether or not we have to hoist the number 8 signal or issue the black rainstorm warning, I hope that we can have the AI models to be explainable in the future. I know that it is still early phase of study how to make our AI weather models explainable, so that we understand why in this occasion we can trust the forecast. Well, we have seen in the past typhoon season that the AI models outperform ECMWF in early indication of a different track from the NWP tracks. So I think we have to use it, but how to integrate human in the process, I think this is also a question very important, and also I think a very important point where we could work with the commercial developers to have our expert in the loop during their development, further development of the AI models. But of course, the threats to the weather surfaces around the world will be that the commercial products are developing very, very fast. So even in the span of a year, we already see new products coming out. For example, NVIDIA coming out and selling their AI products. So it could be maybe in five years or even 10 years time, maybe some of the weather surface maybe go out of business. I think that's well, actually when I was the director, they remember I always told them about the threats to the weather surfaces, and I think now it's really is coming. But how we make the best use of these new technologies in our operation and in our services for the public, I think is all the more important at this point in time. So I hope we can foster closer collaboration with these big giants. And for Hong Kong, I think Huawei may be a very and Fuxi, yeah, I think we need close collaboration in order to compete, right? Thank you.
Yeah, thank you. That's well said. Yeah, definitely. I can see you are actually actively collaborating with those tech companies. So, Professor Tang.
Thank you. Thank you to invite me here and having these great discussions. And I'm not an expert in AI, and I will talk more on a science point of view and on the university aspect. So I view this AI is more of an opportunity than a threat, as firstly, we have more and more PhD students graduating, so it's opening more job opportunities to us, right? This is a good thing for our young scientists and students. And I think the technology companies and universities or scientists have their own advantages that we can collaborate. The big companies have this kind of huge computational resources and tools that are updating very fast, right? And that huge resources it's not easy for each universities to directly apply to training with these large supercomputers and with the current limited funding. But our scientists, we can do some more things, like for example, we can bring up more ideas, more science questions to how to use these tools to help us solve some questions we are caring about. And we can also help to evaluate the results more thoroughly or more scientifically, which how to demonstrate these results is good or not in different point of view. Also, to explain, like Dr. Wang mentioned about all those physical-based machine learning, but I still don't know how good the physical explanation is, and if that really satisfies our curiosity in the physical mechanisms. I think in this several aspects, it still needs a lot of scientists measured in expertise in atmosphere sciences, meteorologists to deep into it to get more ideas of all these details. Yeah.
Yeah, thank you. Yeah, definitely we can see there are also unique strengths and maybe advantages from university side to help actually advance this AI applications for weather forecasting. So speaking of that, so I want to know, since we already have quite a few very good performing AI models. So do those models provide actually science insight into the precipitation or the atmospheric sciences? Actually, also how can we actually translate our knowledge actually gained from physical models to build better AI models? So this kind of two-way interactions. So I want to hear your kind of insights in this.
I would say that this is a question I'm very interested in, and I don't have any answer. I think this is something that we can put a lot of effort to explore, right? And yeah, I really have no idea what it would be, but it will be something that we need to explore.
Me too. I'm not the real one. I can get a full picture, but I think as a mission, I also during my presentations talk about get human to understand, to improve. So maybe I recall a dialogue with the Pangu weather model team that we visited the office a few months ago, that how they get the idea on doing the Pangu weather model. I got the impression that because basically they would like to know how AI technique, because this has been in the computer science for many, many years. But weather system is really very high dimensional. But of course, I know it started from a very young guy in Huawei that he just learned meteorology by himself and do everything. So, but the beauty is they would like to know how this AI model has the physical, maybe in terms of mathematical jargon, how it relates to the symmetry and the characteristics of the weather involvement. So they would like to dig into some kind of this idea, although they haven't say in like that way. So the thing is, we have to get more understanding by using different types of model, because they know they based on various formalism. But at the same time, to those students right now, you have actually a lot of opportunity here, because they paved the way now to devise or maybe to formulate several kind of possible approach that the AI technique can encapsulate the complexity of the atmospheric process. Although in the past we rely on very sophisticated mathematics, very sophisticated numerical methods, but now they open the way that you can do simulation very fast once the model is trained. Although training model is difficult. But at the same time, you can generate various scenarios and various applications that you can study more about the models. And of course, what the current generation of students maybe had a more emphasis or more focus is on how you can apply the physics or apply your understanding of those technology to push it forward in terms of, for example, a better physical model or better physical formulation in the model. They also talk about the physics-informed mechanism, like they have the several types of parameterization in the AI model. And then the second thing is how they produce an ensemble, because ensemble now, even for ECMWF, they got about 100 ensemble members, physical model. But with AIFS, I know they are now trying to put up 1,000 now. So it's a kind of a big field of which you can apply your knowledge or use your new research on a very powerful tool for you to test it out, to do the simulation of the atmosphere, even for the climate as well. So in old days, climate model is very low resolution. But now if you have sufficient good enough data to train the climate simulation, perhaps we can go for kilometer scale climate simulation using AI model in near future. But that also leads current generation of students, maybe professor, to think about any better way to even a clever, more powerful, more elegant, more resource-saving approach to run a very high resolution. What I want to say is another way, another aspect is that now when you train an AI model, you need a lot of GPUs. That's very energy consuming, not green, not sustainable. So I think another big area is to devise a much more advanced, maybe concise and elegant and clever enough way that we can solve this problem. It's a much more economical approach. Thank you.
Thank you. Yeah. Professor Zhang.
Yeah, I really like the question. How to make AI explainable. Of course, we don't have the answer today, but I hope that we will have the answer very soon. But I think for me, I think I would ask some question first. How to get there, I don't know. First question is, we know that the AI models did better in track forecasting than the NWP. But when I try to understand, just based on my limited meteorological knowledge, for example, the Babinka typhoon that just hit Shanghai a few days ago, we see the NWP model has left, the bias to the left. So it's just hit Fujian, and then gradually it corrected the track forecast. But the AI models already put Babinka close to Shanghai. So obviously the AI model has something better, but we don't know why. If we look at the intensity forecast, the AI models didn't give any good intensity forecast, frankly speaking, compared to the NWP. So the difference in intensity may not explain this better performance in the track. So what else? So I think we need to think very hard how to answer this question. So this is, I think, question number one. And of course, the other question is whether or not the AI models has learned anything about the physics, so that in the future they could tell us what they have learned, why they make such a forecast based on their understanding of physics. But apart from this, I think we also need to ask the question whether they outperform the NWP models because of their memories of the past events. This actually, we have the analog system, so-called analog system for years. But in the past, we were limited by the availability of data. But now we have the ECMWF reanalysis data. And so very naturally, we should be able to get very good analog forecast system. So the AI, I think, served this purpose well, I would say. But we still don't know whether their better performance is due to analog memories or something else. I think we need to try hard to answer these three questions at least.
So yeah, I agree. This is a very difficult question. We probably don't have an answer now, but hopefully after the 3 days, we would have more clear answers. So actually, I want to ask a more specific question. So in terms of nowcasting of extreme rainfall, I know there's still room to be improved. So I think training a very good AI model needs very good data, like a high resolution, high accuracy data. So from your experience, what is the spatial or temporal resolution of the data, or what types of data you think that can really help maybe have better nowcasting of extreme rainfall?
I think the primary one should be sufficient, good enough, and good quality radar data, ring gauge network. Satellite data depends on your domain. I think if you would like to focus on the geographical coverage, then of course those geostationary satellites should be the good choice. But in terms of really would bring into the intrinsic characteristics of convection, then you better look into some more multi-sensor satellite, getting you the microwave or infrared going to the cloud structures in order to getting more realistic rainfall measurement. And I think this has been done by many meteorologists in the past decades using traditional machine learning technique. By combining multi-sensor input, geostationary and polar orbiting satellite. And then I think Personally, I see there's a potential is because although we don't know why AI model can do the right job, but AI model did give us some skill in representing the large scale weather phenomena together with the NWP. Perhaps from forecaster perspective, you can treat it as one of the ensemble member, or the AI ensemble generates some realistic ensemble that hopefully may give us the background atmospheric condition why extreme rainfall will happen. Although the rainfall forecast itself from the model may not be good, but at least the general pattern or maybe some atmospheric process represented by physical model together with AI model will give us a more complete picture why we have extreme weather. So I would say this will be very important. And back to zero, quality is important. So we spend a lot of effort, although I showed you very, very good result today. But basically, there are a lot of days and hours that we spend behind to clean the data, to process the data, to extract the key information that will be useful for us to train the model effectively.
Thank you. Yeah, please.
Yeah, recently I got interested in AI in general and the development, and also I read some books, for example by Li Feifei, one of the originator of the ImageNet, which facilitates the rapid development of deep learning. So I think the success story was that she spent a lot of efforts in creating a large database of the images with categorization of input by humans. So I just wonder whether we could reproduce this success story in our nowcasting AI. Of course, 7 years of radar data is already a lot in terms of the size, but if we think about the time period, it didn't capture the heavy rain last year, the so-called century, black rain, and it didn't capture the 2008 rainstorm, which was the previous record for the 1 hour rainfall. So I think the size of the data is one critical aspect if we learn from ImageNet story. Another thing is, of course, whether it's purely data-driven or we have some human knowledge also embedded in the training data set. So we have to tell the AI system that, okay, this image is a dog, and we have hundreds of them, different dogs, different kind of dogs, different colors, and then the AI will learn. But for our radar data, I don't think we have yet to tell the AI system that oh, this is a frontal case, cold front, and this is a squall line, and that is from a typhoon. And or even at HKO, we have the so-called X files. Whenever we see two intersecting squall lines, that could mean really heavy rain in the middle or at the crossing. So I think we need to tell the AI about all these cases and categories. So how to do it, I don't know. It may need a lot of expertise, input from forecaster, but I personally think this is the way to go.
So we have our own ImageNet.
Yeah.
I did a lot of work on the observational data set, and what I feel is that observations is kind of quite not enough and not complete. for example, for the upper air measurements, the radio sound, we only have the regular radio sound launching twice per day, and each radio sound stations are like several hundred kilometers apart. Of course, we have a good quality reanalysis data using the data simulation that the circulation are pretty good, reliable. So I think this is also the basis that the big AI weather models have a good success. But when we go down to like extreme weather, severe weather forecasting, so we are like highly rely on radar images. We have a high resolution and fairly good coverage on the precipitation, right? But still, for that kind of severe weathers, we have some information missing, like the circulation, right? The wind, we don't have the good observation for the mesoscale, microscale circulation related to the convective systems. And also, also we have some variables we are interested in, but we really don't have good observations, like fine-scale cloud structures, heating profiles, and even turbulence scale. Yeah, I'm wondering how the AI can help to supplement our data set if there is no observation. I don't know. This also brings me another question extending from that, is that do we really need a comprehensive observations of the system? Because for physical models, we are trying to put everything in it: air source, clouds, precipitation, winds, temperature. But for AI models, currently they are more target specific, right? Weather models focusing on the rain only, and the tropical cyclones only looking for the tracks. So they only need a part of the information to train the data and achieve the specific target. But in the physical model, we are trying to predict everything: temperature, wind, precipitation, and at everywhere. So even now we see the comparison between AI model and the physics model. There are some kinds of unfair in it, in my opinion. Yeah, but I don't know. Is it also a good way to just design different models to targeting on different specific things, or do we still need to have some kind of comprehensive model, even in AI, to get everything together? Yeah, I think this is also an interesting question.
I interpret what you said is actually the data to train the AI model may not just be observation, could be some kind of combination of observation and model results, or maybe selective variables, not all the variables. Yeah.
Yeah, I think currently the AI models just use selected variables to train, right? Yeah, I don't know if we could or we need to input everything we can get to get more comprehensive predictions. Maybe this is also related to climate modeling, where Chris will talk in the afternoon. Right.
Yeah. Okay. So yeah, in the interest of time, I wouldn't ask my question now. So maybe open the floor for any people who want to ask questions to Dr. Wang or Professor Song and Professor Tang. Okay. Any questions? So I saw David raising hand.
I can follow up with a question I asked earlier to Dr. Wang, which is the pathway to probabilistic prediction and the possibility of connecting that to things that would be of interest to the climate modeling efforts. As you move to a probabilistic prediction, you might be able to get beyond the 2 hours, even in the precipitation forecasting business. And so I would be interested to hear you elaborate on that, and then our other panelists chip in as they like.
Thank you. I appreciate it. It's very inspiring. And during the discussion, I think I mentioned one of the past work that has been done before by some group is trying to play with the loss functions that they consider certain kind of fractions of correct forecast and the correct negative forecast in some way. But I think, yeah, you're right. We have been checking some potential probabilistic application of the AI nowcasting, but we do see, because of the blurriness problem, sometimes in the probabilistic formulation there may lead to the overconfidence forecast for some small or medium rainfall threshold, but without any signal on the extreme rainfall. So you're right that perhaps using the probabilistic formulation of the loss function in the loss function, or even in the AI model formulation, in some way we could stratify or try to address those signal leading to the development of extreme rainfall by preserving the occurrence based on a training data set, or together with segmenting the past cases according to various scenarios, we can do the other way around, is to try to use the probabilistic formulation to forecast a big pattern of the radar leading to potential of extreme rainfall, and then apply those idea like diffusion approach to add the small scale features in the model. That may be one of the possible approach that I'm now thinking of. Thank you.
Well, I just want to supplement. Actually, I saw your probabilistic forecast of the lightning. That one, I think, definitely is something would contribute to lightning for nowcasting based on both AI and also the actual sensors. Yeah.
Well, thank you for the panel. I am Hayden. I'm an undergrad student here. I had a question for especially those at the HKO. Because unlike academic research, where it's more, experimental to, more practical situations, what is the risk of being wrong? And how do you have the judgment and confidence when it comes to situations like this?
Talk about nowcasting is not a problem. We can see the result very quickly, whether it's true or not. So, well, but somehow we have to learn from failure. For example, maybe it's coming to be much more an issue where we move into sophisticated approach like diffusion model and physics-informed model, because with the physics, what we put or what we can do with the limited resources, we can think of those manageable approach, like the principal mechanism, like what I tried before, using the conservation equations in the moisture to gauge the loss function. But somehow, in reality, this is not the only primary reason why it works. So, next step, maybe you have to think about whether you can have some stochastic component to give you better idea. But when you don't try, you never know. And nowcasting has a big advantage is once you try, you will know you are right or wrong very quickly. And I think it's a work to do this and do a lot of verification. I always stress on verification is because somehow you see a very fascinating published papers on nowcasting, but I will always ask the question, is the balanced data? So I mean, academic side, you can think of very fascinating, very clever, very advanced technique. But in reality, we have to put all these things into practical and verify, understand why it works in some cases and why it don't work in some cases.
Just have a follow-up, especially to Professor Qiming Shen. When you've been the director, there are definitely cases in your tenure where you've made a misjudgment. And when it comes to, for example, in the future where you rely on these AI models, if there is a misjudgment, would you likely take the full responsibility, or could you just blame the AI? And what's the ethics of that?
Yeah, this is exactly what I want to say about. I think first, whenever we launch a new service, we will show people the verification result. Okay, it is 60% correct or 70% correct on average. So this is our skill level, and so. But the most important thing is that when our forecast goes bust, then we need to explain to the public why this time it went wrong. For example, I have several cases that in the past that I issued the number 8 signal, but no wind in Hong Kong because the typhoon just veered a little bit to our east and died quickly after landing. So we have data to prove that it was strong, but then because of the slight deviation of the track, we didn't get the resulting high winds. So the most important thing is we can explain using data and using science. So now the problem is for AI. That's why I'm so concerned about the ability to explain the AI results. If we can't explain it, then, well, you have to find some other explanations for your wrong forecast. No matter what, you have to explain it. Because we, as the government department, we have to be accountable to the public.
Thank you. Yeah, it is a very difficult kind of endeavor. We do make mistakes, but we learn from our mistakes. So actually, in the interest of time, I couldn't take more questions, but feel free to actually find our panelists and just interact, ask questions. So next, thank you. We will have a small gift for our panelists, so I'd like to present them and just show our appreciation.
Okay. Thank you. Thank you.
Okay, thank you. Yeah, thanks a lot. Yeah. So next, we will move on to a kind of short presentation of our precipitation forecast model in comparison. In fact, it's just a small hackathon on precipitation prediction from this